We use the integration over the single variable functions in order to find the surface areas of the solids which are obtained by rotating some curve around the x-axis, as in this case, or around the y-axis, or around some lines. Now let's discuss how we can obtain the area of the surface, which is given with some multivariable function. We would like to find the surface area in this case using the double integration. The basic idea of this would be to split the surface area into the small tangent planes, and by finding the sum of those tangent planes, we would find the area of the surface. The basic idea is to choose some sample points on the surface and create the tangent planes for all of these points. Let's look to this tangent plane more precisely. So if we're given some sample point Pij, we would like to create a tangent plane and find its area. In order to do this, we need to create a t vectors in the direction of the tangent line in the x direction and in the direction of the tangent line in this direction. So the vector A in the direction of the tangent line in this direction would have the following components, and the vector B in the direction of the tangent line in the y direction would have the following two components. Please note that fx and fy are the partial derivatives of the surface in the x and y direction. They basically mean the slope of the tangent line in this direction and the slope of the tangent line in this direction correspondingly. So if we're given the t vectors, if I multiply these t vectors as a cross product a to the b, this would give me some vector. But if I take their magnitude, it would give me the area of the parallelogram, which is obtained by these t vectors. So let's multiply these two vectors as a cross product and let's find its magnitude. So the vector A is given with the three components. Let's look to this vector more precisely. So I see here the I component and the k component. There is no j component, so that is why the vector A is given like this. And the vector B is given like this, with the three components, where the first component is 0 because there is no I here. So let's multiply these two vectors as a cross product. In order to do this, we need to find the determinant of the matrix, where I write the ijk on the first row, delta x 0, fx delta x on the second row, 0 delta y, fy delta y on the third row. Then we need to evaluate the determinant of this matrix. So the determinant of this matrix would be minus fx multiplied to the delta x, delta y multiplied to the I, minus fy multiplied to the delta x, delta y multiplied to the j, plus delta x, delta y multiplied to the k. If I take out the delta x and delta y from all of the three components, I would have minus fx I minus fy j plus k multiplied to the delta a. Then the area of the tangent plane would be the magnitude of this vector. And in order to obtain the magnitude, what we need to do is we need to take the square root of this part, which is fx in the square, plus fy in the square root of the second component, plus the square root of the third component, which is 1 in the square, multiplied to the delta a. So this is the area of one tangent plane at the point ij. And in order to find the overall surface area, we would just sum all of these tangent planes. We would sum all of these tangent planes with respect to the I from 1 to the n and j from 1 to the m, where n and m are the number of the points on the x and y directions. So obviously we would find the surface area approximately if we did the limit number of the tangent planes over the surface. But if we increase the number of the points on the surface, and basically increase the number of the tangent planes on the surface, we would get more precise and precise result. Basically, if I take the limit or double limit of the sum when n goes to infinity and m goes to infinity, tij, this would be the double integration over the region d of the integration of this function, which is the partial derivative of the f in the square plus partial derivative of the y in the square plus 1, and it is integrated with respect to the dA. So let's do an example in order to see how we need to calculate this. So let's say we would like to find the surface area of the part of the surface that lies about the triangular region T. Let's look to this triangular region T more precisely. So this triangle is given with the 3 points, with the 3 vertices, 0, 0, 1, 1, 1, 0. And let's define first of all this region T. So this region T is given as the points x and y, where the x would change between the t constants, right? So from 0 to the 1. And the y would change between the t functions, between this line, which is 0 line, and between this line, which is y is equal to the x line. So now what we need to do is we need to integrate this surface. The surface is given as the equation z is equal to the x squared plus ty. We need to find the partial derivative of the z with respect to the x, it would be tx. Then we need to find the partial derivative of the z with respect to the y, which is t. Then we need to substitute everything to the formula. So the surface area is the double integration over this region t of the square root of tx in the square, which is the partial derivative of the z with respect to the x, plus t in the square, which is the partial derivative of the z with respect to the y, plus 1, and we need to integrate this with respect to the dA. So more precisely, we can write this integration as, so since y is changing between 0 and x, we would integrate this firstly with respect to the y from 0 to the x, 4x squared plus 5 dy, sorry. Then we would integrate this with respect to the x from 0 to the 1. So let's discuss this integration firstly. So when we integrate this function, 4x squared plus 5 from 0 to the x with respect to the y, we would look to this function as a constant because there is no y there. So its integration would be 4x squared plus 5, just simply multiply to the y, and we need to substitute the 0 in x, it would be simply x multiplied to the 4x squared plus 5. Now we need to integrate this function, x multiplied to the 4x squared plus 5, with respect to the x from 0 to the 1. So please note that I see the function and its derivative. Here I would make the substitution, right? So let's substitute u as 4x squared plus 5. Then du would be 8x dx. And I see x dx in 4x squared plus 5 here inside my integration. So let's put this here. So if the x is equal to the 0, it would be 5 here. And if the x is equal to the 1, it would be 9 here. Multiplied to the square root of u multiplied. So x multiplied to the dx. So x multiplied to the dx is simply du over 8. So the integration of this function would be u in the power of 3 over 2 multiplied to the reciprocal of the 3 over 2, which is 2 over 3, multiplied to the 1 over 8. And we need to put the values 5 and 9 to here. So if I substitute the numbers, I would get 9 in the power of 3 over 2 divided to the 12 minus 5 in the power of 3 over 2 divided to the 12. So if I take out the 12 from the brackets, it would be 1 over 12. So 9 in the power of 1 over 2 is 3. 3 in the power of 3 is 27 minus 5 multiplied to the square root of 5. This is the surface area of this object. Let's consider another example. Find the area of the part of the paraboloid, which is given with the equation z is equal to the x squared plus y squared, that lies under the plane, which is given with the equation z is equal to the 9. So this is the plane, z is equal to the 9. So we need to find the area, surface area of the paraboloid under this plane. So in order to do this, we're going to use again the double integration over this region D, where this region would be a circle with a radius 3. When I choose this surface z is equal to the 9, and substitute the z to here, it would be x squared plus y squared is equal to the 9, which gives me the area, which gives me the region here, right? So x squared plus y squared is equal to the 9. It's a circle with the center at the 0 and 0 and the radius 3. So I would integrate, in order to find the surface area, I would evaluate this double integration over the region D, where the D is a circle. So let's find a z. So z is equal to the x squared plus y squared. So that is why the partial derivative of the z with respect to the x is tx, and its partial derivative with respect to the y is ty. If I substitute everything to here, it would be the double integration over the region D of the 1 plus 4x squared plus 4y squared with respect to the dA. So if I would integrate this with respect to the x and y, it would be really difficult for me to integrate this. So let's convert everything to the polar coordinates and try to integrate this more easily. So in order to convert everything to the polar coordinates, we need to use this equation. So in order to convert everything to the polar coordinates, we need to use these two equations, where the x squared plus y squared would give me simply r squared. And the d in the polar coordinates, so this region D in the polar coordinates, would be defined as the points with the coordinates r and theta. And all the points inside this region have a distance from the origin between 0 and 3, and the angle changes between 0 and 2 pi. So this double integration would be equal to the double integration in the polar coordinates. So 1 plus 4 x squared plus y squared is the r squared. And do you remember, so the dA would be r multiplied to the dr d theta, and the r would change between 0 and 3, and theta would change between 0 and 2 pi. So let's evaluate this integration first. So in order to do this, I would see here that I would use the substitution. U would be equal to the 1 plus 4r squared, and du would be equal to the 8r dr. And I have the r dr here, so that is why r dr would be du over 8. So let's integrate this. It would be a square root of u and its integration multiplied to the du over 8. The integration of this would be u in the power of 3 over 2 multiplied to the reciprocal of the 3 over 2, which is 2 over 8. 2 over 3 multiplied to the 1 over 8. And we would have u in the power of 3 over 2 divided to the 12. So actually, I can define the borders of this integration as well. So if I substitute the 0 to here, I would have 1. And if I substitute the 3 to here, which is 37. So then I need to put here 1 and 37. If I substitute the 37, it would be 37 multiplied to the square root of 37. If I substitute the 1, it would be simply 1, which is minus 1 over 12. So now we need to integrate this. So this is the integration of this part in the integration. We need to integrate this 37 minus 1 over 12 from 0 to the 2 pi with respect to the theta. So since this is the constant, its antiderivative would be this constant multiplied to the theta. It would be simply 2 pi multiplied to the 37 square root of 37 minus 1 over 12.